Okay, welcome back, everybody. So, yesterday's lecture ended with a warning concerning an application of this theorem. It was our big theorem with a lot of parts. So, just to remind you, our big theorem was this fundamental theorem of complex calculus. Okay, where if we have a function that's continuous on some domain D, we have the following statements are equivalent in that they're either all true or all false. Okay, and so the statement that this f has an antiderivative, big F, throughout D, that implies the following two statements, and this implication goes in both directions from all these statements, so all these are equivalent. So this is equivalent to having this FTC-like formula for computing an integral in terms of an antiderivative. Okay, so this told you many things, other than giving you just a convenient way of actually computing this contour integral. It also told you that this integral didn't actually depend on the contour in question, since it really only depended on the values at the endpoints. Right, so it depended on the values of this antiderivative function at the endpoints. And so we could actually write this contour integral like this, basically ignoring the specifics of the contour itself and just focusing on the endpoints. Okay, so that's nice. And this, of course, also told us, right, as a special case immediately following from this, is that the integrals around closed contours where these endpoints are equal all have value 0. So if you have a closed contour lying entirely in this domain D, then if f has an antiderivative throughout D, for instance, then its contour integral around any closed contour lying entirely in that domain is 0 by this formula. Okay, but what's also nice, right, so it is easy to see it in this direction, but what's also nice is that we have a statement going backwards that if somehow we came about the knowledge that we were dealing with a function such that its contour integral around any closed contour lying entirely in some domain was 0, then we would also get these things. So namely, we would get that it has an antiderivative, and we can apply this formula. Okay, this will be important later in this lecture. There will be an example of where we use this backwards direction here. Okay, so it's very important that these are equivalent, right? TFAE, if you like. Okay, I may be writing that a few more times in this course, so you're used to this from linear algebra stuff, right? Okay, so this was nice, being able to go forwards and backwards here. But, so we saw some examples of using this to make our lives easier, but I gave a warning at the end of lecture, and the warning was the following. So right before I talked about this warning, we did an example of 1 over z squared, I think. And we saw that 1 over z squared had a nice antiderivative everywhere except the origin. And so if we were dealing with any closed contour that missed the origin, then we were good to go to use that theorem and be quickly done. Okay, but notice that if we try to do the same thing with this function, there is an issue here. Okay, and the issue is that the antiderivative of this, of course, is this multi-valued function log z, right? Now, log z is going to be fine, say, if we're dealing with a contour that is, we're going to take, say, a circle, right, centered at the origin. This log z is fine, and it is the antiderivative of 1 over z everywhere except along this branch cut that I've put in red here, right? So, and notice that no matter if we take this thing and we rotate it, right, no matter where we make that branch cut, I'm going to intersect the point of this circle. Okay, and so not only is it not the antiderivative of little f at a point on the branch cut, it's also not, it's not even defined, right? It's not even defined along a branch cut. Okay, so at any point where this contour intersects that branch cut, this condition of the theorem is not going to be satisfied. You're not going to be able to use it. Okay, and so how can we get around this? Okay, so I say that I can't proceed here, at least normally, right? Maybe I'll say yet. Okay, but there's a way that we can deal with this. And so to see how we can deal with this, let's let's consider kind of the following idea. Okay, so let's say we are stuck in this issue here where we are taking this curve C that is we'll say it's circle of radius 2, I think is the exact example we were using before. So if we have circle of radius 2, this has a parameterization in terms of theta. This is just 2 e to the I theta, and this parameterization, we'll say theta lives between minus pi over 2 and pi over 2. Okay. All right, and so if we have the circle, of course, looks like this. Okay, so here's this circle that I'll call C. This is the thing that I want to compute this integral, this contour integral along. So 1 over z dz. This is what I want to compute. But the problem here is, so for instance, let's say if I look at the principal branch. Okay, so then the principal branch of log, so principal branch of log z is capital L log z, which is defined to be the natural log of r plus I principal value of theta, right, principal value of the argument. So this principal branch is my modulus of z is greater than 0, and big theta is strictly between minus pi and pi. And so this principal branch has its branch cut over here, right? So here's my branch cut, and my positive x-axis is included there. Okay. So then, what is it? Oh, I have written C here. I've jumped ahead of myself here, right? Let's not do this. This is where we're headed. Okay, but I've kind of jumped the gun here. So this is theta, of course, between say 0 and 2 pi, right? Is the full circle C here that we're looking at of radius 2. Okay. All right. But if we look at the principal branch, here's my branch cut, so there's an issue here at this point. Okay. So what is the idea? Again, I want you to note that this issue here of the branch cut touching the curve is not an issue per se for the integrand itself, right? So the integrand itself has no issue anywhere on this branch cut except at the origin, but we don't care about the origin because the curve's not touching there anyway. Okay, but there is an issue with the antiderivative, right? So this is the problem. The problem is that it's the antiderivative that has an issue at this branch point on this curve. That's the problem. Okay, so it's not the integrand itself, it's the antiderivative of the integrand. Okay, and so how do I deal with this? The idea is split C into pieces and use different branches. Of log z as your antiderivative on those pieces. So we want to use this as the antiderivative of 1 over z on those pieces. So the idea here is to, say, split this curve in such a way that it doesn't intersect the branch cut there on the first half. And then for the second half of the curve, we'll choose a different branch of the log so that taken separately on each curve half, we will have a full antiderivative. And so the first half I want to take is the one I accidentally wrote first, which is this right half. Okay, it's this right half of C. We'll call that C1. Okay, notice that if we take this curve, this does not intersect the branch cut. Okay, so maybe I will redraw that on the next page. Okay, So taking the principal branch of log, what I have is the following picture. There's the three axes that I actually have. Here's my branch cut. And my curve C1 is this one, which you will notice does not touch the branch cut. So this is my C sub 1. Okay. So if I take this as my C sub 1, of course, this has a quick parameterization. This parameterization, like I said, is the one I accidentally wrote earlier. So this is 2e to the I theta, where theta is taken from minus pi over 2 to pi over 2. So theta is between minus pi over 2 and pi over 2. Okay. So we're taking the principal log. Right, so log z is ln r plus I big theta, where r is positive and big theta is strictly between minus pi and pi. Okay, so on this C1, if I'm looking at the integral, the contour integral over C1 of 1 over z dz, well then now notice I can use my theorem. Right, I can use my theorem. Note, big F of z, which is the principal branch of log z, is it's an antiderivative everywhere on C sub 1 for little f of z, which is 1 over z. Right? This issue of worrying about this log not being defined on this branch cut doesn't matter because the branch cut doesn't touch the curve. So this is an antiderivative everywhere on this curve. And so we can use the theorem. Right, so we can use big theorem. Okay, and so using big theorem here, what do I get? Rewriting this is the integral from, so this goes from minus 2i to 2i. Right, so this is the integral from minus 2i to 2i of 1 over z dz here. Okay, and so this is my principal branch of the log of z evaluated from minus 2i to 2i. Right, what is that? All right, so this is just principal log of 2i minus principal log of minus 2i. Okay, coming down here, what is that? So principal log of 2i, that is just by definition. This is a natural log of the modulus 2i, which is 2, plus I times this principal argument's pi over 2, of course, because you're here, right? And this is minus natural log of 2 minus pi over 2 times I. All right, so you have the natural logs of 2 cancel, and you have I pi over 2 minus I pi over 2, so this is pi times I. Now, we actually computed this earlier in a different way, just straight up from the definition of the contour integral, right? So using the parameterization itself, we actually straight up computed this, okay? And so that was another alternative way of computing this. But this is to show you that you can actually use that, our version of FTC for complex functions, you can use that here as well, as long as you're careful. Now, of course, we're not totally done yet, right? We're not totally done, because if we go back to what it is we were actually trying to do, we have only dealt with half of this original curve that we were interested in. So we want to deal with the other half. But what is the problem with the other half? The other half intersects this stupid branch cut. So what do I do? If I'm considering the other half here, and I will draw it fuzzy to indicate that's what I'm looking at now. So if I'm looking at this other half of this circle, I want to take a branch of the log that makes its branch cut, say, over here instead. So I want my branch cut to now be disjoint from this other half that I'll call C sub 2. Okay, so how do I do that? Well, let's draw the picture first, and then we can think about how we're doing this. Okay, so let's draw the picture. So what I have is my three axes like this. I want my branch cut to be the positive x-axis, and my curve C2 is going to look like this, right? So the points are still the same. This is 2i and minus 2i. Here's my curve C sub 2. How do I choose the branch of the log that does it? All right, so first of all, for C2, how do I parameterize this? So C2 has the exact same parameterization. I just changed the window the parameter lives in. So I'm always happy when I can do that. So this is between pi over 2 and 3 pi over 2. So theta is between pi over 2 and 3 pi over 2. Okay, but what branch of log z do I take? So I want to consider the branch natural log of r plus I theta, where r, of course, is always greater than 0. And the branch I take is the one for theta strictly between 0 and 2 pi. I want to cut the positive x-axis out. So I want theta to be strictly between 0 and 2 pi here. So this is the branch that I take. Okay. So once I do that, now computing this contour integral along C sub 2 yields the following. So again, this is the integral now from 2i to minus 2i. Why? Let's be careful here. The original orientation, of course, it's positively oriented. It's going counterclockwise, and so this is the direction. Right? On the other half of the curve, it was going from down to up. Right? So it's going from minus 2i to 2i. Here, it is going from 2i to minus 2i. You can just check that by seeing what the values of theta are doing. So this is actually the integral from 2i to minus 2i. All right, so this is a question of orientation here of 1 over z dz. Now I can use my theorem in the exact same way. I'm just going to put a star here. Right, I'm not going to write out what I did before. So this is log z using this branch. I'll call star, my star branch here. This is log z evaluated from 2i to minus 2i. Okay, and so this is log of minus 2i minus log of 2i. Right? And so this is natural log of 2 plus, on this branch, this is natural log of minus 2i. The argument is 3 pi over 2. So it's 3 pi over 2 times I minus natural log of 2 plus I times pi over 2. Right? And so I get natural log of 2 cancels with natural log of 2. I get 3 pi over 2i minus pi over 2i, so I get pi I again. And so now, if I want to go back and answer this question, what is this contour integral over the entire circle C? Let me go back and... All right, this is what I wanted to compute, this thing, over this whole curve C. Well, I can now just sum these contour integrals that I've computed piece by piece here. So this is the sum of the contour integrals of this integrand over the pieces C sub 1 and C sub 2. But that's just pi I plus pi I, so 2 pi I. Okay. And so we can use this even when it's a little bit tricky to do so if we're really careful by considering different branches and splitting our curve up if need be. Okay, so that's one example of how this sort of thing works. Okay, so I want to do one more application of our theorem before moving on. I'm going to actually skip the proof of the theorem because it's kind of long and involved, and I don't think much use comes in applications that we're going to be doing later out of going through it. But if you're interested in it, I can tell you where it is in the textbook. But yeah, I'm not going to actually cover the proof of the theorem. So I wanted to go over one more example here. Okay, and the example that I wanted to do is I want to compute the contour integral over contour C of the square root of z dz, where the branch of z to the 1/2 taken is, we'll call this, so fz is square root of z. The branch we're going to take is e to the 1/2 log z, which is square root of r e to the I theta over 2, where theta is, so r is positive and theta is strictly between 0 and 2 pi. Okay, so our branch cut is the positive x-axis. Okay, and along with the origin. And C is any contour from z is equal to -3 to z is equal to 3. Okay, that, except for its endpoints, lies above the x-axis, we'll say. Okay. All right. So, what does this picture look like? Well, I've already said that my branch cut is the positive x-axis in the origin. So there's my branch cut. What my curve C looks like is, if this is -3, maybe my curve C does something like this, and then comes over here to 3. Okay. Alright, so here's my C. Okay, maybe it's got some corners in there, but we'll just say that it looks like this. Okay. What is the issue that prevents us from just doing this, right? Why can't we just apply the theorem immediately? Well, the thing is that if I want to, say, look at this thing generally and think about this function more generally, right? So I'm not thinking about a particular branch. There should be nothing wrong with this integrand, right, along this curve. This should be absolutely fine. The problem is that the branch in question, right, that we're using for the integrand is bad at this endpoint. Okay. And so the integrand itself is piecewise continuous on this curve C. Okay. It's piecewise continuous on this curve C. Therefore, the integral exists. Okay. But this branch that we've chosen, it's bad for this curve because, you know, there it is, right? There's the bad point, right? And I don't want to deal with that. So then you might just say, what if I choose another branch? Right? What if I choose, say, another branch? How would this affect things? So what if I choose another branch of my integrand? So let's say instead of an f, I have like an f sub 1 of z that I define as, this is always square root of r e to the I theta over 2, but I choose my branch such that r is greater than 0, and I make my branch cut, say, the negative y-axis. Right, so theta is strictly between minus pi over 2 and 3 pi over 2. And so I make this my branch cut instead. Okay. Can I just swap this out? Right? Can I just swap this with this thing and say that those integrals, however I do them, using whatever branch, would be the same? Well, I have to be careful here, right? So what I have to do, how I have to be careful, is to basically compare the values of these things and make sure that they match up. So first of all, the whole reason I switched to this branch is because this thing is continuous everywhere on C, right? So this is continuous everywhere on C. And what is very, very nice is that its values along C match up with the values of this branch, except at this point. That's the only place they differ, right? And so that's fine, right? Having different values at a single point is not going to matter in the integral. Okay, and so yes, this can be swapped out. Okay, and so we can swap out this branch of our integrand for this one instead, and there's no issue here because they agree on this curve. Okay, and so this is the really, really nice fact. I can do this in multiple ways. So if my curve looked different, like if I had the same exact curved sort of thing, except it was below the x-axis, I could make a cut, say, up here instead, and I could use a different branch. But now, what is the antiderivative of this thing, of this other branch? Well, the antiderivative of this thing is actually 2/3 z to the 3/2, which if I write this out, this is 2/3 times r times square root of r e to the I 3 theta over 2, where the branch I'm on is the same as my, this is what determines the values of theta here. So theta is again strictly between minus pi over 2 and 3 pi over 2. Okay. Notice that this is the antiderivative of this thing everywhere, okay, along that curve. And so now I can actually compute this in exactly the way that I want to. So the integral along this curve C of the square root of z dz can be done by integrating from minus 3 to 3 this replacement branch, right, f sub 1 dz. I can use my theorem. So this is big f sub 1 of z evaluated from minus 3 to 3. So this is, rewriting this, this is 2 root 3 times e to the I times 0 minus e to the I. That's 3 pi over 2, which is 2 root 3, 1 plus I. Okay. All right. We did a similar example of computing this contour integral in a different way before we talked about antiderivatives. Okay. And as I said, we could have done this replacement thing in a different way if the curve in question, say, passed under the x-axis instead. Okay. We could have cut out, say, made another branch cut instead, maybe the positive y-axis, right? So that's the idea. Okay, we are going to skip the proof of our big theorem. our FTC, fundamental theorem of complex calculus. We'll call it FTCC. We're not going to prove this. The proof is in section 45, I think, in the textbook, if you're interested. So that starts on page 146. Is where that starts. Okay, and it takes a few pages, takes a little bit of work to do this. You have all the tools that you will need already in order to actually go through that proof, but it would just take us too long and take away from what it is we're trying to do in applying this stuff. Okay. All right. And so next, we focus on the situation arising in condition 3 of the Beek theorem of FTCC. Okay. Namely, the question of when integrals or contour integrals along closed contours are 0. Okay, so this is of particular importance to us, and you're going to see why this is so nice. Okay, going to be a lot of examples that kind of illustrates exactly what it is that's nice about this. Okay, so our next big named theorem is called Koshi-Gorsat. Okay, so but before we kind of talk about this, or especially before I state it, I want to do a quick investigation. So here's an aside from Calc 3. So from Calc 3 material, especially line integral stuff. So line integrals in the plane. We can recast a lot of what we're doing, okay, in notation that's consistent with how we wrote things in Calc 3. So of course, I'm not going to define all these things, but you know them by now. Whenever I'm talking about a contour integral like this, the strict definition here is that I have some parameterization, z is equal to z of t. T lives in some parameter window, right, of the real, some closed interval a to b. So this is the integral from a to b of f of z of t. So I'm plugging in that parameterization here, times z prime of t, times the derivative of that parameterization dt. So this is, all this is my definition of line integral. Okay. Okay. All right, which is how I defined contour integrals. But if we write f of z component-wise, right, as functions of u and y, or dependent on functions of, of u and v, which themselves are functions of x and y here. Okay, and if I write this parameterization z of t, if z of t is written as x of t plus I y of t, okay, then when I write this, right, what am I actually doing here? Well, let's rewrite all this. Then this contour integral f z dz is the integral from a to b of f of z of t, z prime of t, dt. And so rewriting it in terms of these things, this is the integral from a to b of f with the parameterization plugged in here is u of x of t, y of t, plus iv of x of t, y of t. Okay, it's a lot of parentheses. times the derivative z prime of t, which is the derivative of these things, so it's x prime of t plus I y prime of t dt. Okay. Now, if I expand these out and regroup terms using just basic algebra here, what's another way of writing this? This is the integral from a to b of u times x prime. So I'm going to suppress the notation here of plugging in x of t and y of t into u and v, because that would just take me too long to write all that. It would be extremely long. I would have to put like 2 sheets end to end or something. So this is u times x prime. I'm going to entirely suppress the dependence on t, minus v times y prime dt, plus I times the integral from a to b of v times x prime plus u times y prime dt. Okay. Now I want to use Calc 3 notation. Using Calc 3 notation, these two line integrals become what? So there was a shorthand notation you used for writing line integrals of vector fields, right? And so a way of writing this in shorthand would be viewing this as dx dt here, right? So the trick to remembering this shorthand, right, was you thought of x prime as dx dt, and then what you did to remember this notation is you thought of this dt thing as canceling out in the denominator, right? You thought of dx dt as being an honest-to-God fraction. You thought of this as canceling out. And so when you rewrote this in terms of line integrals, you'd say, oh, this is the line integral over c of u dx, right, minus v dy. This was just a convenient notation that allowed you to quickly plug in what was needed to compute line integrals. Plus I times the line integral over the curve C of, again, similarly, v dx plus u dy. Okay. And so what we have really done here is used Calc 3 notation, and we have replaced f here with u plus iv, right? So we replaced f with u plus iv, and we replaced dz with this dx plus I dy. That's literally all we did here, and did the obvious algebra, okay, if we're using notation a little bit. Okay, of course, we are assuming that this is happening over contour, but actually everything we did here is valid over just any nice enough curve, okay, not too much, not too many conditions on C is required there. But anyway, okay. So why do we want to write things like this? Recall, there was a very, very nice fact that is a special case of a special case. It was one of the big named theorems you did at the end of Calc 3, right? It was the first big named theorem you talked about. Specifically, it told you how to compute a line integral over a curve as a double integral over the region that the curve bounds. Okay, so recall Green's theorem. Green's theorem said that if you had a line integral of a generic vector field, so p dx plus q dy, that you could compute this as a double integral over R of the x partial of q minus the y partial of p dA. Okay. let's do a quick picture here to illustrate the relationship between this C and this region R that I'm talking about. So the way that Green's theorem is stated, and you might recall that Green's theorem required something. It required, so the statement of Green's theorem as it's stated requires that the curve be positively oriented. So say I have a curve C like this, and it is positively oriented in this way. Okay. This curve is the boundary of a region R. So the region is the region R. The boundary of R, written like this, is equal to this curve. And Green's theorem said that, so Green's theorem, it's just a quick reminder, said that if you were doing a line integral over this curve of a vector field with components P and Q here, so this is a vector field on the plane, then you could actually compute this as a double integral over the region R, the x partial of q minus the y partial of p. Now, the thing is, the way this is used in Calc 3, of course, was line integrals you're kind of taught are kind of nasty and bad. And when possible, you would usually want to use this to actually compute this line integral via a double integral. Which in the examples that you tended to do in Calc 3, the double integral was far easier. And so that was the direction that this was usually used in. We are going to use this for another purpose, because we want to use this in conjunction with Cauchy-Riemann equations to actually show that we have something nicer going on here. Okay, and so first of all, the function f that we're talking about is actually continuous in this region R in question. So we're talking about this f is continuous on the curve, and it's continuous on the region R because it is analytic. Okay, it is analytic here. So we are doing this setup in such a way that f of z is analytic along the curve itself and the interior of the curve. Okay, and so the idea here is that we want to restrict ourselves to contours that are simple closed contours. So note, C is a simple closed contour. Okay. All right. And so we assume that f is analytic on C and all points interior to C. So all points on the inside of C. Recall, a simple closed contour. So a closed contour means it closes up, it's a loop. If it's simple, it means it has no self-intersections. Okay, and so maybe it looks something like this. It could look a little nastier, it could have corners and stuff, but it still is a loop of this, right, that has some finite number of corners, okay, at worst. And so these are the assumptions. It turns out these are very, very key to us. This is going to basically, this is all we're going to need, right? And now we're going to be carried through by all of this buildup, okay, that I've started here. And so, going back, if we assume that f's analytic on C and all points interior to it, then it's analytic on C, it's analytic on the interior, which is this region R, okay? And so, if it's analytic on R, it's certainly continuous on R. If it's continuous on R, then its component functions are continuous on R. Right? And the other assumption that I'll call assumption star, assume f prime is also continuous on C. Okay. well, I should say on f prime is continuous on C and in R. Okay. So this might be a little bit confusing of an assumption because you actually might think that this is implied. It turns out that it is implied from this first condition that I've boxed. Okay, but we don't know that yet. Even though I've told you some things in passing of where we're headed and what it means for a function to be analytic, we actually haven't proved that stuff yet. And so while you kind of already know that being analytic is super nice, and I've already told you being analytic means like screw first derivative. You have all derivatives if you're analytic. Okay, so of course f prime is continuous, but we don't know that yet. Okay, so we're pretending like that I haven't told you that. We don't know that yet, and so we're making this assumption. Okay, this is the assumption that Cauchy made when he originally was deriving this result that we're going through right now. Okay. And so we use Green's theorem. And we apply Green's theorem to this way of writing this contour integral. So we apply Green's theorem to this thing that I'm going to put a red star next to. So we apply Green's theorem to this. When we apply Green's theorem to this, it allows us to rewrite both of these line integrals using Green's theorem and taking x and y partials of these things. So here, in this first integral, p is going to be u and q is going to be minus v. In this second integral, p is going to be v and q is going to be u. Okay. So applying Green's theorem to these two integrals separately, I won't go through that entirely. I'm just going to write what happens when you do that. So applying Green's theorem to red star, what do we get? We get that this contour integral of f is the double integral over the region R of minus v sub x minus u sub y dA plus I times the double integral over R of u sub x minus v sub y dA. Now, before you freak out and say, oh, I don't really remember how to do double integrals, right? I totally forgot how to do that. Don't worry too much, because what are our CR equations, right? What's our Cauchy-Riemann equations? You should know this by now. U sub x is equal to v sub y. U sub y is equal to minus v sub x. These both must be satisfied because f is analytic everywhere we're interested in this, right? Well, if u sub x is equal to v sub y, this integral is 0. If u sub y is equal to minus v sub x, this is minus v sub x plus v sub x, so that integral is 0. So this is 0. Thus, what have we shown going through all of this? So we have shown the following. Okay, if f is analytic in R and on the boundary, right, and f prime is continuous there, then these were our assumptions. This was my first box. This was my second box. This was my assumption star, right? Here, this is my assumption star. Okay. Then the contour integral over that contour that is the boundary of my region R, of f of z dz is equal to 0. So actually, if I have a function that is analytic on a region and its boundary curve, and its derivative is continuous there, then when I integrate over that boundary curve, that boundary contour, I get 0. So this is a result due to Cauchy. Okay. we don't have a name for this result because we're going to show something that is very, very nice. That actually condition star is not needed. I'm not going to go through the proof of this, okay? But it turns out we can do better. Gorsat was the first to notice that condition star is not needed. This is not needed. Unnecessary. We can actually remove it. Why is that important? So a quick aside. So why is that a big deal? The answer is that ultimately we are going to use this fact that I'm about to state as the Cauchy-Goursat theorem, that we don't need to assume this continuity to show that if you are dealing with an analytic function defined in the way we defined way back in the first week of classes, if you're dealing with an analytic function, you automatically get the continuity. It turns out that it comes with it. Okay, and you can't have an analytic function analytic function on some domain that has a first derivative that's not continuous on the domain. That can't exist. Okay, and it is going to be used further to show some of these really, really nice facts that I've been dropping hints about the entire course so far, which is that analyticity gives you a ton of really, really nice stuff in a way that you just do not get in real analysis, right? So doing the same sort of things with real valued functions, this just doesn't work this way. Okay, so we're actually going to show that the derivative of an analytic function is analytic itself. Okay, so this will let us show, ultimately, let us show that if f is analytic, then f prime is analytic. But if f is analytic, then f prime is analytic. Well, then by this same statement, f prime prime is analytic. And f prime 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 is analytic. Right? And so on. This is the really, really nice thing that you do not get, right, in real analysis. This is like the exact opposite statement that you can expect when you're dealing with a real valued function. Okay, so this is extremely nice. So ultimately, the fact that this is not needed, it's because you automatically get it. Analyticity gives you this. You don't have to assume it. Okay, it is actually a consequence of it. And so I'm going to state the combination. So these combine to yield the following. So this is the Cauchy-Goursat theorem. Now, we proved Cauchy's version of this, okay, using Green's theorem. We're not going to prove the general version of this because it would take too long, but again, I'll show you where the proof is. And so what is the Cauchy-Goursat theorem? If a function f is analytic at all points interior to, and on a simple closed contour C, then the contour integral over C of f of z dz is equal to 0. What's kind of a way of looking at this intuitively, maybe, and trying to understand what this is kind of saying, and how a statement like this is kind of different in some way than what you've seen before. Well, if we think of integrals, contour integrals along closed contours as being an important type of integral that we want to compute for complex valued functions. What this is saying is that if your function is analytic, right? If the function in question is analytic, which means it is complex differentiable, it has a complex derivative on a neighborhood, some neighborhood of each point in the domain. Well, it has contour integral on a simple closed contour of 0. And so basically any, quote, nice function that you do a contour integral along a simple closed contour of has contour integral along that contour of 0. So basically all the nice functions, if we're defining nice as being analytic, right, having a complex derivative everywhere you want, then its integral is 0. Okay, this if you consider the integral of on a simple closed contour to be an important type of integral, and it is. Okay, so this is a little strange, right? This might be a little strange intuitively. Quick example, of course, is if C is any simple closed contour, and it doesn't really matter how it's oriented because this thing is supposed to be 0 in this case, so the orientation is ultimately not going to matter. Then the integral over the contour C of, say, e to the z cubed dz. Right, looking at this thing, maybe it's unclear exactly how you would go about integrating such a thing in a normal way. Well, this is 0. Right? Since if we're looking at the function, it's the integrand e to the z cubed, this function is analytic everywhere. So you're done. That's it. So by Cauchy-Goursat, that integral is 0 because it's analytic everywhere. Okay. Don't even need to check continuity of the derivative because it turns out that doesn't matter. That's actually a consequence. Okay. So this proof you can find starting on page 152. This is section 47 in the textbook. Again, the proof, you can absolutely understand everything going through the proof. There's some annoying bookkeeping that has to be done, and there's some things that will only make sense when you see the pictures drawn out for you. But the textbook has nice pictures of what goes on in the argument, and it's not too bad to go through. It's not too intimidating. But ultimately, the proof itself is not going to give us anything as far as what we want to do, the kinds of applications we want from this. Okay. And so, basically, we want to apply this or versions of this in various contexts. So we seek to apply this in various contexts to obtain other versions. Versions of it that are either slightly more general or just apply in a different setting. They're either more general or we apply them to a specific setting where it allows us to compute an integral or say that two integrals are equal when we're interested. So this is actually going to give us a really cool way of going back and seeing that some of those earlier contour integrals we computed could have been computed in an easier way. We could have actually made things easier on ourselves. Okay. All right. And so the first thing I want to do before trying to apply Cauchy-Goursat or talk about other versions of it, I want to give a definition. So, but first, a definition. If you have ever encountered any topology, you are well acquainted with this term, but if not, that's okay, because for our purposes, we have a simpler, pun intended, way of describing this. So this is the notion of simply connected. See, now you see the pun. So we want to talk about a simply connected region. Okay, so a simply connected domain D is a domain such that every simple closed contour within it encloses only points of D. Now, the topological definition might seem a little bit more intuitive than this one, because this one, when you first hear it, doesn't really, it's hard to actually see what this is doing until you understand what is not a simply connected domain. So let's look at examples. So let's let D be the following domain. Let's let D just be, say, the interior of a ball. Okay, so here's D. All right, so here's my D. All right, so why is this a simply connected region? Well, if I draw any simple closed contour in D, so there's one, here's another one, here's another one, here's another, and another, maybe intersect some of those. All of these, no matter how I draw these simple closed contours, they never enclose a point that is not in D. Now you might say, well, I'm having a really hard time trying to come up with a region maybe that fails this. But what if we consider a punctured disk? So let's take a disk and then let's put a hole in it. Okay. And so we have the set D prime that's this like annular region, this like open annulus or something. Okay. And so, while some simple closed contours only enclose points of D prime, here's one that encloses points that are not in D prime. Right? Notice, here's a point that is not in D prime, but it is enclosed by that contour that I sketched. So this is not simply connected. And this is simply connected. Okay. Now, I can give you the topology equivalent definition of simply connected, which is that we'll call a domain D simply connected if every simple closed contour in it can be continuously deformed to a point while remaining in D. Okay. So what do I mean by that? So for instance, in this case, all these loops that I draw, I can suck them up to a point. I can shrink them continuously in a continuous manner, okay, such that I'm not doing any breaking or anything. So I can just shrink them to a point, okay, and I can, at every single point, I'm just going through points of D. Notice that I can do that for some of these in D prime, but not any curve, right? No contour that contains these bad points that aren't in D prime can I shrink to a point. When I try, the best I can do is I can get really, really close to this interior boundary. But I can't actually totally shrink these to a point, right? I can't totally shrink them to a point because D prime doesn't contain that inner part. Okay, that's the topology intuitive way of thinking about it. Okay, this is the notion of simply connected domain. Now, why am I defining this now? So it turns out that this, considering a simply connected domain, allows us to throw out another assumption in Cauchy-Goursat. Okay, so the main point that this is the entire reason we're giving this definition now. Okay, this is also going to have some nice application when I am going to move to talk about some things that are pretty topology heavy, but I'm not going to require any knowledge of topology to do this. Everything you need to know from the topology is going to be given to you, by me in this course, so you don't need to go anywhere else for it. So what is the main point? The main point, if the region in question is simply connected, and a lot of the regions we're going to talk about are simply connected. So if the region in question is simply connected, then the contour in Cauchy-Goursat need not be simple. And so we will have another type of theorem that is Cauchy-Goursat adjacent, we should say. I won't have a name for it, but it's we'll call it Cauchy-Goursat enhancement 1, right? So say theorem, we'll call it maybe Cauchy-Goursat, like for simply connected domains. That's kind of a mouthful. Maybe I should have just called it Cauchy-Goursat 1.1 or something. Okay, so if f is a function that is analytic throughout a simply connected domain, D, then the integral over any closed contour C of f of z dz is equal to 0, where C is any closed contour C lying in D. Okay. So the proof of this is if C is simple, it's easy. It's just Cauchy-Goursat. Just Cauchy-Goursat. Okay. If C is not simple, then it has, say, finitely many intersection points. We can split this up and apply Cauchy-Goursat in pieces. Okay. But if C intersects itself infinitely many times, there are more subtleties involved that I'm not going to get into right now. You can see an example of some types of strategies that can be used to kind of straighten some of these out in the textbook, but I'm going to leave this unresolved here. But keep in mind that this is we have basically done this so long as it only has finitely many self-intersections. So by the time you're dealing with infinitely many self-intersections, that's already a pretty nasty curve. But it turns out that you can manage to deal with this too. It just requires a little bit more effort. Okay, that I'm not going to go into. If you want to do this for more general types of curves like this, then yeah, it's going to take. Unfortunately, it's just going to take a little bit more effort. But I can give you actually even the book has a reference for this. So if you're interested, let me know, and I can actually give you a reference for looking those things up. That also reminds me that during the last office hours, there's some really good questions about analyticity and what it meant for Cauchy-Riemann, whether or not Cauchy-Riemann was sufficient or just necessary. And there were some counterexamples that are not that intuitive. I'm going to rewrite those examples. I'm actually going to tech them up, and I will post those things as well as references to where you can find proofs of those facts to work through them, because it's not entirely simple to go through those. And I had to look them up. I didn't know those counterexamples off the top of my head. Okay, so let me check. Have I run out of time? Is this? No, we still have a little bit. Okay, so that's good. So let's see how we can apply this to compute some nice contour integral. Let's see. Be any closed contour lying on the circle modulus of z is equal to 2. Lying, inside. I should say lying inside the circle modulus of z is equal to, i.e. lying in the domain D, which is modulus of z is strictly less than 2. Okay, then this contour integral of, say, integrand is z e to the z over z squared plus 9 to the 5th, right, dz. It's a pretty nasty integrand. How would you ever compute that? Oh, wait. I don't need to. Why do I know that's 0? C is any closed contour. The open disk of radius 2 is simply connected. So what do I need? So C is any closed contour, check. Simply connected, check. Let's go back to my theorem. Say I need my integrand, of course, to be analytic throughout this simply connected domain. Okay, is it? Well, where are my possible singularities for this function? Well, the only singularities of f of z are at the zeros here of z squared plus 9 to the 5th. Those zeros happen exactly at plus or minus 3i. Okay. But they are outside this disk, i.e. outside the disk D. So f of z, the integrand here, is analytic on D. Okay. Okay, this thing is analytic on D. Okay, it's analytic because it is a combination. It's this rational combination, right, of analytic things. The only possibility for non-analyticity here, since all these things, all these components are analytic, everything I'm doing here is analytic. E to the z is multiplying z times e to the z. Polynomials are analytic. Dividing by polynomial is perfectly fine, so long as, and exponentiating to an integer power, that's good. Polynomials are analytic. The only time dividing by polynomial is bad is when you have zeros, but those zeros are outside the disk, so this is analytic on D. And so we can apply this enhanced Cauchy-Goursat, and we get that that integral must be 0. Doesn't matter what C is, right? So if I draw a picture here, my disk D looks like this, right? Here's my disk D. Here's my singularities. They're outside the disk, so I don't even care about them. This curve C could look like this. Right here's C. Okay. Doesn't matter. Right? Doesn't matter at all. So back in my C could be even nastier than that. This integral is 0. So this is really, really nice. Okay. There is a corollary of this that is extremely nice. And first, when I write this, you're going to be like, why do I know that? Why is this a corollary of this fact? So corollary to this theorem is a function that is analytic throughout a simply connected domain D must have an antiderivative everywhere in D. What? First of all, try to think to yourself for a second whether or not that is true in the reals, right? Right. So try to think for to yourself for a second if this is true, if the function in question is a real valued function of a real variable. Okay. So a function that is analytic throughout a simply connected domain D must have an antiderivative everywhere in D, I should say. When I say it has an antiderivative in D, I mean everywhere in D, but I'll throw this in just to make sure you know. Okay, so what's the proof here? Well, if f is a function that is analytic throughout a simply connected domain D, then let C be any closed contour in D. Then by our amplified Cauchy-Goursat, so by Cauchy-Goursat 1.1, okay, what do I get? The contour integral of such an f over the C is equal to 0, right? And this is true for any closed contour in my region D. Okay. Let's go back. Let's go back. Where's our big named theorem? Hold on, here we go. I mentioned at the beginning of the lecture, in our big named theorem, we were going to use the fact that the following are equivalent. These things are either all false or all true. These implications run in all directions. And so, we have the statement that if C is any closed contour in the domain D, the contour integral over that C of the f is equal to 0. Thus, we are satisfying condition 3. The integrals of f of z around closed contours lying entirely in D all have value 0. Yes, we satisfy condition 3. From FTCC. But if we satisfy condition 3, all of these have to be true. Namely, condition 1 has to be true. This implies 1 is true. i.e., what does 1 say? F of z has an antiderivative throughout D. F of z has an antiderivative everywhere in D. And that's it. That's my proof. Okay. Another corollary. If F is entire, remember that means that it is analytic on the complex plane, then F has an antiderivative. Okay. How do I prove this? The plane is simply connected. So we're done by the previous fact. Okay. So if a function's entire, that means it's analytic on the entire complex plane. Thus, complex plane is simply connected, so it's analytic on a simply connected domain. But this previous corollary has an antiderivative, okay, on that domain. So these facts are really, really nice. And these facts are not something that you're going to get in real analysis, right? So this is something that's not true, and I urge you to actually go back, think about this setting in real analysis, and think about what that would mean, right? If you could do your calculus integrals in this way, okay? If you always had antiderivatives, if you satisfied these conditions, and then you'll maybe appreciate how radically different this is. Okay. It's especially funny because, of course, in the first couple of lectures, you kind of get the feeling like, oh, complex analysis is kind of, sort of like real analysis. I'm just like hiding everything as these component functions u and v, blah blah blah. But it, and it seems like that at first, right? It seems like it's a glorified version of the calculus you're used to. But these differences start creeping in, and now we're, the foot is on the gas pedal maximally, where, the following theorems we're going to see are so completely different from anything that exists in real analysis that you have far passed beyond the point where, you're doing things that are radically different. You are now way beyond that. We're going to be talking about things that are so alien and foreign to real analysis that it will, hopefully make your head spin in a good way. So anyway, I think that's it for today's lecture. We'll pick up here tomorrow at the normal time, so I will see you all then.